Esther is one of Micha's many extremely strong students, and I think that this group still kind of holds together and keeps working together, and amazingly solves problems that looked completely hopeless in the late 1980s and early 1990s. So I follow Esther's career with admiration, and in so many different areas, including epsilon nets. She proved beautiful things. So I am very happy that she accepted our invitation. So thanks, Esther.
Okay, so thank you, Janusz, for the nice introduction, and thank you for inviting me. It's an honor. I'm going to talk about recent developments on intersection searching, which is part of the realm of range searching. But beforehand, I'd like to give just a few personal notes about Ricky and Eli. So I knew them, both Ricky and Eli, since I was a student, but I was closer to Ricky. And when I was a postdoc in Quran for a couple of years, I met Ricky quite often, especially in the geometry seminar where I was a participant and sometimes also a speaker, a seminar that both of them, Eli and Ricky, organized. And personally, I remember Ricky as a very optimistic person, always smiling, never complaining. He always used to say, take it easy. And professionally, I didn't work with him, but over the last 2 years, when I started working on the algebraic methods, I learned to appreciate his influential book about algorithms in real algebraic geometry with Basu and Roy. Okay, so now to the scientific part of this talk. What are intersection searching? So this is a family of problems in range searching, and it goes as follows. So the input objects consist of a family S. These are simply shaped objects in RD. For example, triangles in free space, as this illustration shows. And gamma is a family of query objects in RD. So, for example, circular arcs. And the intersection searching problem is to preprocess S into a data structure that supports intersection detection queries with respect to the objects in gamma. Intersection detection queries, that usually includes intersection counting, where we would like to count how many objects from S does the query gamma intersect, or report all such objects. This is intersection reporting, or shooting, that is reporting the first object of S intersected by gamma if it exists. This is more suitable when gamma is a family of arcs. And there is another version, intersection emptiness, or just intersection detection. That is, you would like to detect whether gamma intersect any of the objects in S. Okay, so I'm going to talk about, at least for most of this talk, or a considerable part of this talk, about a concrete example, which is the example for ray shooting. So ray shooting amid triangles in free space. And here the input consists just of n triangles in free space. And the ray shooting problem is to preprocess T into a data structure such that given a query ray rho, it efficiently reports the first triangle hit by rho if such a triangle exists. So in this picture, this is an example for ray shooting with respect to a polyhedron in free space whose all facets are triangles. Okay. So this problem is motivated by computer graphics because it has several applications in computer graphics, such as ray tracing and hidden surface removal. But theoretically, it is interested in its own right. And there has been a lot of activity in studying these problems for about 3 decades by many people. This is just a partial list of the researchers who has been working on this problem, and I'm also presenting a table of the state of the art. So this includes Pankaj Agarwal, De Berg, Dobkin, Halperin, Kirkpatrick, Matuszek, Overmars, Sharir, Snoek, Van Creveld, and many more. So I'm summarizing the state of the art, but this is just a partial list of the known results. So in the plan, ray shooting in a simple polygon. So Hershberger and Suri, they showed a data structure of linear storage, and a ray shooting query can be performed in logarithmic time. For segments in the plan, this has been studied by a number of people, including Matuszek and Agarwal and Sharir. They gave a trade-off bound where the storage is M and the query is N over root of M. And the storage bound, this trade-off bound means that for any value M of the storage, which is roughly between N and N square, we get a different bound. I mean, the more we invest with the storage, the faster query we obtain. So if the storage complexity is about N square, the query time is polylogarithmic. And in the other extreme, if the storage is roughly linear, the query time is about root of N. So O of star, this is a notation I'm going to use in this presentation, which implies that the actual bound also includes a factor of N to the epsilon or a polylogarithmic factor, but the O star notation suppresses these factors. Disjoint arcs in the plan. So Agarwal, Van Creveld, and Overmars, they show the data structure of linear size and root of N query. And in 3 dimension, so there are a number of results. For convex polytopes, Dobkin and Kirkpatrick, they introduced a data structure by a hierarchical decomposition. They introduced a data structure of about linear storage and logarithmic query time. For plane and half planes in 3 dimension, Agarwal and Matuszek, they introduced a trade-off bound of M and N over M to the 1/3. This is based on a parametric search mechanism. So I'm going to give slightly more details about this result. And for triangles in 3 space, this is the setting that I am discussing. This has been studied by a number of people with a trade-off bound of M for the storage and N over M to the 1/4 for the query. And here, this trade-off bound implies that for storage M to the 4th, the query time is logarithmic, and when M is roughly linear, the query time is about N to the 3/4. Okay, and in higher dimension, there are also several bounds studied by Agarwal and Matuszek. For hyperplanes in D dimensions, the storage trade-off bound is M and N over M to the 1D. And this is the trade-off bound for ray shooting in convex polytope. Okay, but from now on, we are going to focus on triangles in 3 space. And a few words about the work of Agarwal and Matuszek. So a key ingredient in their work is to reduce the ray shooting problem to segment emptiness problem, or segment intersection detection problem via a mechanism of parametric search. So the segment emptiness problem, similarly to what I've defined before, so I'm just doing it in slightly more detail. So here, the problem is defined as follows. Given a set gamma of geometric objects, you would like to pre-process them into a data structure so that given a query segment S, we can efficiently decide whether it intersects any of the objects in gamma. Okay, so this is a segment intersection detection. Some people call it segment emptiness. This is the same, it has the same meaning. So this implies that once we have an efficient segment emptiness mechanism, we can obtain an efficient ray-shooting mechanism. So the performances are similar up to a polylogarithmic factor, which follows from the parametric search mechanism. All right. And what is the situation about triangles in 3 space? Like I said before, the current rate-of bound is m and n over m to the 1/4, which and this bound follows from a bound on a 4-dimensional range searching problem. So range search problem was defined by Micha in his talk. In such problems, we are given a set of points in 4 dimensions. We would like to pre-process them efficiently, such that given any range, you would like to detect intersection, count intersection, and so on. Okay, so what about this question for triangles? So this problem suffers from the curse of 4-dimensionality for lines in 3 space because of the reasons that lines need 4 parameters to be defined. That is, this is an illustration. This is a line in 3 space. And we collect the x and y coordinates where it intersected the plane z equals 0, and the x and y coordinates where it intersect the plane z equals 1. And these are overall 4 parameters that uniquely define this line. And based on that, and based on several other considerations like orientation test, let's say pretty much standard considerations, we can map this problem to R4, where triangle edges are mapped to points in 4 space and query rays are mapped to surfaces in 4 space. And therefore, we can reduce the problem, we can actually map this problem to a range searching problem in 4-dimensional space. And this eventually leads to the trade-off bound m and n over m to the 1/4 on the storage and the query time. Okay, so this is the state of the art. But a wishful thinking is not to go up to 4 dimensions, but stay in 3 dimensions. Okay, and so what we hope is that since triangles in 3 space are flat objects, then perhaps ray-shooting amid triangles should be resembled to the case of planes in 3 space. And for planes in 3 space, we already have the bound for ray-shooting, the trade-off bound m and n over m to the 1/3. So the big question is whether it is possible to reduce this problem to ray-shooting amid planes in 3 space. So, so getting such a reduction, getting such a bound is, we believe it's kind of unrealistic. But what we did manage to get is to show such a bound for a specific value of m. So we do not get the whole trade-off, but for one specific value of m, we get the same behavior as that of planes in 3 space. And this is one of our main results. So here we apply what is called pedestrian approach in 3 space. Such an approach in the plane was also applied by Hershberger and Suri. So the problem is not lifted to a 4-dimensional space. We stay in 3 space. And what Micha and I managed to show is that for such a collection of n triangles in 3 space, we can obtain a data structure of size and the pre-processing of n to the 3/2, such that ray-shooting queries amid these triangles can be answered in time about a root of n. Okay, so this is a significant improvement. So for m, roughly equal to n to the 3/2, the previous bound, the one with the lift into 4 space, resulted in query time of n to the 5/8, and now we managed to improve it to root of n, which is better. And this theorem, this data structure, is based on the mechanism of polynomial partitioning, which Micha presented in his talk, but I also would like to add a couple of words of mine. So this is a geometric divide and conquer mechanism, which is very general. And the input is a finite set of semi-algebraic sets in D space. In our case, S is just a set of lines in 3 space. And the goal is to obtain the composition of space into open simply shaped cells, such that each cell meets only a small fraction of the objects, and therefore this is a divide and conquer mechanism. And as Micha mentioned in his talk, this has been used quite a lot in order to solve incidence problems in geometry and other related problems. But recently, it has also been exploited to solve algorithmic questions such as range searching and point location and eliminated depth cycles. And this work is just another application. It's another part of the demonstrating the power of the polynomial partitioning. Okay, so let us focus on polynomial partitioning for lines in 3 space, and this is based on an important theorem by Larry Guth. So he showed a much more general theorem for varieties, even for semi-algebraic set in this space, but we use it only for lines in 3 space. This is the way that I'm demonstrating it. So given a set L of n lines in 3 space and a degree parameter capital D, Larry Guth showed that there existed real trivial polynomial f of degree order of D, whose 0 set Z of f, these are all the points in space where the polynomial is equal to 0, partitions the 3-dimensional space into order of D cube open cells, each of which is intersected by at most n over D square lines of L. Okay, so this is a worst case bound. Like Micha said, getting this bound on average is easy, but getting it on the worst case, this is the main contribution of Guth. And this picture is just an illustration of such a polynomial partitioning. So the 0 set in this case, in this picture, is a quadratic. As a matter of fact, this is an hyperboloid of 1 sheet. And we have 5 lines. 2 of them intersect only the outer exterior, the outer portion, and the rest, the remaining 3 of them intersect both the inner and the outer. Okay, so this is Guth's theorem. One issue in the polynomial partitioning theorem is that it does not give us, at least not directly, a bound on the number of lines that lie on the 0 set. So in principle, the 0 set may contain arbitrarily many lines or even all the lines. And this can happen when the 0 set is a ruled surface, a surface ruled by lines. So these are 2 pictures demonstrating singly ruled surfaces. The plane is infinitely ruled by lines. So it may happen. And in such a case, each application has to deal with it in its own way. In our case, we have to separately handle the case where a query ray lies on the 0 set. And we have to develop a separate mechanism for that. Okay, what about the algorithmic implications? So it is also possible to construct such a polynomial partitioning efficiently. So this is a paper of Agarwal, Ornov, Zal, and myself from 2019. So we showed that, again, this result is more general, but restricted to the case of lines. We show that for a set L of n lines in 3 space and a degree parameter D, one can construct a polynomial partitioning f of degree at most D for L in expected time, which is this. The time is linear in n and exponential in the degree D, which implies that when D the degree is constant, the expected running time is only linear in n. So I would like to make just a few comments about this result, about this paper. So that result was presented at the CG Week Workshop 2019 that Boris Arnov, Pankaj Agarwal, and myself organized. We organized a workshop, Algebraic Method in Discrete and Computational Geometry, dedicated to Ricky Pollack. Okay, so just to make this note, and now let us continue. So our pedestrian approach goes as follows. So we construct a polynomial partition in F for the 3n lines containing the edges of the input triangles, and we do so recursively. The query arrays are handled in two separate cases. The first one is where the query array is not contained in the zero set. In such a case, the pedestrian approach just implies that we walk along the cells that meet the query array row, and in each of them we solve the ray shooting problem recursively. And then we return the first hitting point that is closest to the origin of row if it exists. And if the ray row is contained in the zero set, then we apply a separate ray shooting mechanism within the zero set, which eventually boils down to a two-dimensional problem. Eventually, what we need to solve in this case is a two-dimensional ray shooting problem amid algebraic arcs. All right, so this is one thing. And another slightly technical ingredient is the recursive construction. So like I said, we construct in expected linear time a polynomial partition in F for the 3n edges of the input triangles in T. And therefore, we obtain a partition of the three-dimensional space into d-cube open cells, each of which is meeting at most n over d square edges. And then we classified the triangles within the cells of the partition. So these are the connected components of the complement of the zero set. So in this picture, one of the cells tau is a torus. And now we classify the cells according to the manner that they intersect tau. So not the cells, so the triangles. So we call a triangle delta narrow in a cell tau if an edge of delta, of the triangle delta, meets tau, the cell tau. Otherwise, if delta crosses tau, but none of its edges does, then we say that delta is wide at tau. So in this illustration, this brown triangle delta is wide in the cell tau, the torus tau, because none of its edges meets the cell. And then we do the following. The number of narrow triangles in tau can be charged to the edges, and therefore it is only order of n to the d square, which implies that they are scarce and we can handle them recursively. On the other hand, the white triangles are more popular, and we need to construct a separate mechanism to handle them and dispose them immediately. So that was one of the main technical ingredients of this work, which I'm not going to show in detail, but just give you some intuition why it is not very trivial. So a wrong intuition is that one may think that we can replace white triangles with the planes containing them. So this is wrong. Why is that? Because of this picture. So this picture is a two-dimensional cross-section of this situation. So this, blue area is the cell tau, and the black segment is a cross-section of the triangle. So if we take the plane that contains the triangle, then we may get a false positive answer because this square array may hit the plane but not the triangle. And therefore, it is not very easy. If we had the property that white triangles behave like planes inside tau, then handling them would be much simpler. We could just get the trade-off bound M and N over M to the 1/3 for ray shooting amid planes in 3 space. What we have managed to eventually obtain is a property more or less along this line when the parameter M for space is n to the 3/2. What does it mean? So if we have a set W of n white triangles in cell tau, we show that there is a data structure of size and preprocessing of about n to the 3/2, such that ray shooting queries can be answered in roughly a root of n time. Okay. And the handling of the 0 set, so here, if the query row lies inside the 0 set, then what we did is just to reduce this problem to a 2-dimensional ray shooting problem. So after a suitable decomposition of the 0 set into XY monotone pieces, here we had to apply what is called cylindrical algebraic decomposition. And project each portion to the XY plane. What we obtained is that the projection of the intersection of every triangle with the 0 set is a curve. It's an algebraic arc of degree D. So this is in the illustration, these are the blue arcs that you see here. And eventually it boils down to this question. Okay, so we showed using a separate mechanism that given a collection gamma of constant degree algebraic arcs in the plane, we can construct data structure of size and preprocessing of about n to the 3/2 that answers ray shooting queries in root of n time. So we had to construct such a mechanism from scratch because we were not aware of previous ray shooting machineries amid the algebraic arcs with similar bounds. But so this is more or less the most technical part of this talk, and the main ingredients that I've just showed, they are what is required in order to prove our result about ray shooting. And now comes the open problems. So a natural open question is to show is whether one can show a full trade-off bound M and N over M to the 1/3 for triangles in 3 space. Currently, we only showed it for this particular value of M. But also one would like to ask whether this technique can be extended to other settings. Simply because the polynomial partitioning is suitable to work in high dimension and also with more general objects. So such extension include higher dimensions. For example, ray shooting a tetrahedra in 4 space, a curvy object, where we replace the triangles by algebraic surface patches, and arc shooting, where the query is contained in, say, in an algebraic curve, or even shooting anything to anything. For example, we have input triangles, but queries are also triangles, and we would like to detect whether any of the query triangles intersect a triangle from the input. Okay, so the first extension in 4 dimensions, ray shooting a tetrahedra in 4 dimensions. So using the pedestrian approach in 4 space and several additional tricks, we managed to obtain a data structure of about quadratic size and square size and preprocessing that answers ray shooting query amid the tetrahedra in about root of n time. And the main motivation for such a question is it comes from kinetic collision detection amid tetrahedra in 3 space. So here we have a set of tetrahedra in 3 space. Each is moving in a constant velocity of its own. Say each is moving along a trajectory line. And we would like to detect a collision by a pair of such tetrahedra. So ray shooting a tetrahedra in 4 space this mechanism answers the question whether an apex of one tetrahedron meets the facet of another tetrahedron. Okay, this is exactly the question of ratio in four space. What about other extension? So when we replace the ray by an algebraic arc, so we call this set of problem arc intersection amid triangles in free space. So here the input consists of triangles in free space. Gamma is a family of algebraic arcs of constant degree in free space. So in this picture, gamma is a set of circular arcs. And the arc intersection problem is to preprocess T into a data structure that supports various intersection queries for the arcs in gamma. And this includes detection, counting, reporting, and shooting. So in another follow-up work with Agarwal, Aronov, Katz, Sharir, and myself, we follow the pedestrian approach for ray shooting. But we also added some new ingredients, some additional tools from range searching and from algebraic geometry, such as the cylindrical algebraic decomposition. And we managed to come with a bunch of results. So I'm going to present to you just a number of them. So one of the results is a data structure of size and preprocessing of about n to the 4/3, which answers arc intersection query amid these triangles in time n to the 2/3. So this is a quite general result, and also I would like to note that the query bound does not, the exponent does not depend on T, where T is the number of degree of freedom of the query arc. We also refer to this parameter as the parametric dimension. It appears only in the constant of proportionality. So a few remarks is that this result also hold if we replace T with slightly more arbitrary, slightly more general objects, something that we call arbitrary plates, and they are planar shapes of constant complexity, like disks or ellipses in free space. And actually, for the case of triangles, we show that the storage can be improved to n to the 11/9 without affecting the query time. Okay. So, Janusz, how much time do I have? Okay.
I think that you have 2 more minutes.
Okay, so I think this will be enough. I'm almost done. And we also showed another extension of this result, I mean, how to improve the query time if we are willing to increase the space. So we got a data structure of size and preprocessing n to the 3/2 with this query time, where T is the number of degrees of freedom of the query arc. So just to give you a few examples of the bounds that we get, for line segments, we know how to replace line segments by lines, and therefore the number of degree of freedom decreases from 6 to 4. And this result implies that the query time is n to the 5/9. So what does it mean? So we can do intersection detection in n to the 5/9. Now, the result about ray shooting already shows that we can do it in n to the 1/2, but this result is more general. Here we can also do counting, count how many triangles does the query segment intersect. And the previous result that I described does not yield the bound for counting, the result about ray shooting, only for detecting and ray shooting. So in other words, this bound is somewhere in the middle, because the previous bound was n to the 5/8, and root n is the wishful thinking bound. And last extension is to triangle intersections. And here we have a collection of triangles, and we'd like to preprocess them such that given the query triangle, we can quickly answer whether it intersects any of the triangles in the input. So we can do so with n to the 3/2 space and preprocessing and root n query time. And as a matter of fact, this result is slightly more general, and we can extend this data structure to support also plate-plate intersection queries. For example, if our input and queries are disk, with n to the 3/2 space and preprocessing, we obtain query time of n to the 5/9. So, there are even further extensions, but I'm not going to present them. Enough is enough. But overall, what I would like to say is that due to the polynomial partitioning technique, this enables us to tackle this problem and obtain this bound. And it was some of these questions were now some of those problems were not studied before simply because we did not have the right tools to attack them. But now we do, and we actually get a flood of results, which is nice. So this is the end of my talk. Thank you for listening.
And Thomas Zalowski is asking, what kind of bound do applications really want? Or is that?
Well, I think that what you would want to get are those bounds as in range searching, but even in range searching, we do not always get the bounds that we want. So there are lower bounds for range searching, and for ray shooting, because of the model of computation, this lower bound do not exactly go through, although the common belief, at least my belief, is that they should be the same. So for instance, for triangles, the bound that we would want to get is the same bound as for planes in 3 space. The trade-off bound is m for space and n over m to the 1/3 for the query.